Welcome to the second part of this session, which is about PERMANOVA, Permutational Multivariate Analysis of Variance. So in the previous session we learned about the parametric multivariate ANOVA, and this method assumes multivariate normality and also homogeneity of variance covariance matrices. So these are really strong assumptions, and generally these assumptions are not met with ecological data, if you remember our sessions on GLMs or distance matrices. So we need a robust method to handle our complex ecological data sets that we have. In this session we will discuss this paper titled A New Method for a Non-Parametric Multivariate Analysis of Variance by Marty Anderson. This paper is a really influential paper. I just checked the citations on Google Scholar and it has more than 4,500 citations. And well, it combines ecological distance measures, like the Bray-Curtis distance that we learned, with a non-parametric approach. On these slides in this lecture I will use a dataset from Germany. It's macroinvertebrate data from the river Werra, and in the river Werra we have around Wacha we have salt brine discharge, which means that the river is really saline downstream of Wacha, whereas upstream you don't have this salinity as stressor. So we might be interested, how do the communities downstream differ from the untreated or unstressed communities upstream. So here's the citation of the data if you want to look inside. However, it's not the original data that I provide here because it's proprietary, but I randomly shuffled it. So, as you learned in the previous part, NMDS is a really useful method to get a first impression of the community data and what's going on the community level. So, here I plot the data using NMDS with the Bray-Curtis distance and a 4-fruit transformation. Why did I transform the data? If I won't transform the data, then highly abundant taxa would drive my NMDS and my distance metric. So here's a figure also from a paper of Marty Anderson, where she shows the different possibilities that we have. So we can include joint absences using, for example, the Euclidean distance. But then we are only focusing on abundance and not that much on composition. If you exclude the joint absences, then we are focusing more on composition. So here it shows the Bray-Curtis distance with a 4-fruit transformation, and as you see, okay, this focuses on composition and the abundance. So this is what we might get out of such an NMDS. So we see, okay, the upstream and downstream sides separate each other. So this is an indication that the communities differ between these and these sides. Or we can look at a spread. We see, okay, here perhaps we have a little bit lower spread than here, mainly because of this point. But in general we would say, okay, this plot strongly indicates that there is a difference between upstream and downstream communities. So we want to test it. We can test this using PERMANOVA. But first, let's go back to the univariate ANOVA. So how was this calculated? Perhaps you might remember from the Univariate Statistics course. So in ANOVA we are partitioning the total variance into variance that can be explained by the groups. and residual variance, so variance within groups. And then from that, so we have variance between groups and within groups. We compute the sum of squares. Then we take the ratio of both. It's called the F ratio, and then we compare this F ratio with an F distribution. And the P value is actually the area under the F distribution that is we get in our F ratio. The multivariate case, it's analog. It's really similar. One difference is that we have two dependent variables and that we don't have a mean. We have a centroid, which is the multidimensional mean. But we are also partitioning the variance. So we have the total variance, which is the distance from the ground mean to the sides. We have also residual variance, which is distance from the group centroids to the sides. And we can also partitioning this. So really analogous. So how is this partitioning done? Well, and that's the main points of this paper. Well, you can use the distance matrix to do the partitioning. So the distance matrix gives us the interpoint distances. So the distance from one point to each other point. However, what you want to have is the distance from the mean to the point. So Marty Anderson's contribution was, and she proves and shows this also in her paper, that the sum of squared distances from the ground mean is equal to the sum of interpoint distances, so all lines here, divided by the number of points. So here's also the formula notation, if you like more the formula notation more than the verbose notation. So how is this done practically? So here we have our distance matrix. It's symmetric, so we look only at the lower triangle here. So the total variance is simply the sum of all distances here divided by the number of sides. We also have the residual variance, which is simply the sum of distances between our groups. Then we can partitioning the variance, build like in the univariate and over an F value, and from this F value we can compute the P value. However, we cannot compare this here simply to the F distribution. Well, why not? The F distribution is only valid for a ratio of two normal variables. However, we are not dealing here with normal variables. We are not even dealing with Euclidean distances, because it can be Bragg-Curtis distance, it can be any distance that you want. So we need another method, and the method that we use here, which is also common, which we also already encountered with RDA and testing, for example, the axis for significance, is permutations. So what do permutations do? They just shuffle the data randomly, because if our null hypothesis, which is there is no difference, is true, then we can shuffle the data and nothing should change. So shuffle our data, and for each shuffling we compute an F value. We do this 10,000 times, and then we compare simply the F values from the randomized data, which is here in blue, with our F value from our original data. And the P value is simply the fraction that is of F value that's bigger than our original F's. Well, this might be a little bit hard to get, so here's another example, a simpler example. So this is just for a t-test. So here on the left side I have an example where the null hypothesis is true, so the null hypothesis is false. The null hypothesis of t-test is, well, okay, there is no difference. However, if you look here, the first row is our data. If you look here, you see that every value in group A is smaller than in group B, so there is strikingly a difference between these two groups. And down here we have permutations. We just randomly shuffle the data. 20 permutations. So you see directly, you can directly distinguish the permutations from our raw data. So this is a graphical inspection. Then if you look at the distribution of differences of means, then we see, okay, our permuted differences are always smaller than our raw data. In fact, this is the maximizes the difference. So here the p-value would be 0 because we have no observation that is bigger than our observed. On the right, we have an example where the null hypothesis is true. So there is in fact no difference between means. So you see here group A has some small values and also some big values. And here's the shuffle data. So you see you cannot really distinguish the shuffle data from the original data. If you look at the histogram of the differences, you see this also here. So here we have, if we permute the data, we have a lot of data points where the difference is bigger than our observed difference. So the p-value would be very high. Well, as I said, PERMANOVA is non-parametric. Well, it's not non-parametric because it uses permutations and does not rely on this parametric assumptions of this F distribution. However, non-parametric does not mean assumption-free. In fact, we also have the assumption that the dispersions are equal. So we can check this visually. So here we just look at the spread. And we'll see, okay, the green points have perhaps lower spread than the red points, but it's not very prominent, the difference. So if we are not convinced, we can make also a formal test of that. This dispersion spread has also a direct ecological meaning. It's really informative. So if you please check these papers that are mentioned down here, then you get some examples. What does it mean? For example, it's a measure for beta diversity. So the more spread we have, the higher the beta diversity is. So to sum it up, we can use PERMANOVA to test differences in community compositions. It's a very flexible approach. We can use any distance measure that we want, not only Bray-Curtis, we can also use chord distances or whatever fits to our data. It's really easy to get, the maths are easy. It's completely analogous to ANOVA. But keep in mind that non-parametric does not mean assumption-free. This is also true for the univariate cases. Yeah, that's the theoretic part. Let's do it in R. So you can find the script on the course web page, and I go through it line by line. So first we load the wagon package, because this is the best package to do multivariate analysis in R. And then we load the data into R. So here first the species data, var underscore sp, and the environmental data. I put this data on the web, and R directly downloads it and loads it for you. However, if this does not work for you, simply browse to this URL here, and then that simply save this as CSV somewhere and then load it manually. So always after loading the data, we inspect the data, we check it using the str function. So here we see, okay, we have 11 observations, rows, and 107 columns, in this case species. So here's the name, species 1, 2, 3, 4, 5, 6, and we see, okay, these are all integers, so looks good. Let's look at the environmental data. Okay, we see we have also 11 observations, but only 2 variables, which is site and position. So position is simply an indicator if it's downstream or upstream. And a first step would be to compute distance matrix. I often get asked, well, how to transform the data. And I would say cannot easily answer this question, but a rule of thumb would be for community data to downweight your highly abundant taxa if you do not want to focus on them, and also want to focus on perhaps more rare species or some composition. And then you should downweight it in such a case that it's perhaps in a scale between 0 and 10. So if we look at the raw data, we see the ranges from 0 to 15,000, which is quite high. If you use square root transformation, see, okay, the range is between 0 and 120, which is also quite high. If you use a fourth root transformation, then we get into this 0 to 10 range. So I decide here to use this fourth root transformation. And here with the vectors function, as you know from the previous sessions, we can compute the Ray-Curtis distance. So I can also look at it. Yeah, not very informative. So here we have every side and the distance. So this would be the distance from Tiefenort to Breitung and from Merkers to Breitung and so on. Okay, the next step would be just to inspect our data, and therefore we perform an NMDS using the meta MDS function from Wagon on this distance matrix. So you learned this in the previous part. And then I just plot the data. Well, I could use plot NMDS, and then it would be give me this plot here, which is not very informative. Could also put type equals text, which labels me the sites, which is a little bit more informative. So we have Buchenau is very similar to Treffort, but Dondorf is very dissimilar to Buchenau. But this does not code, or we have to know which side is upstream and downstream, so it's not so good. So I make here a plot where I color the points depending if they are upstream or downstream. So I first create an empty plot, type equals n, which says, okay, just draw me the axis and the axis labels, but no points. Then I specify the colors that I want to use. Well, I have two group levels, upstream and downstream, so I specify here dark red and green. And then I add the points. So using the points function, it says take the points, the coordinates of the points from the NMDS object, make the points a little bit bigger, make them filled, and for the color, choose from dark red or green, depending on position. So the position has two levels, downstream and upstream. So the first position, downstream, would be dark red, and upstream would be green. Yeah, so we get this. Well, and Wagon has a lot of decoration functions to make these plots much more nice. Also the RDA plots, the biplots and so on. Perhaps just check out Gavin Simpson's blog from the bottom of the heap, where he has a lot of examples how to make nice ordination plots. So here's an example of his blog. So check it out, it's really useful because we won't cover plotting here. So what I do here, with Audi Spider, this just connects all the points to the group means. So here the NMDS object is our points, and we said, okay, what are our groupings, which is the position variable, and label equals true just says that it puts here downstream and upstream the labels. The hull simply draws me a hull around this points. So this adds also information so that we can interpret this. And here we clearly see that the hulls are not overlapping, so there's a clear separation between upstream and downstream. Finally, you can also put a legend, and then you have the figure as it was on my slides. So this plot indicates that we have a difference between upstream and downstream. So let's perform a PERMANOVA. PERMANOVA can be done with Wagon using the Adonis function, which is a really nice name for a function. So it uses the formula interface that you should know now, and the dependent variable in front of the tilde or weakly line is the community matrix. In this case, I for-foot transform it. And after the tilde, we have the independent variables, which in this case is just the position. We specify that we want to have the pre-Curtis distance and how often we want to permute this. The result is very similar to what you know from the univariate ANOVA. So we get the residuals, the total variance, and the variance explained by position, the sum of squares, an F value, and the P values for this. So here in this case would be significant. This says, well, the communities differ statistically significant between upstream and downstream sites. Moreover, we get an indication of explained variance. So in this case, 30% of the total variance is explained by this factor, upstream, downstream. As I mentioned, this p-value is based on permutations. We can also inspect the permutations. So here, the vertical line would be our original value. And these points are all shuffled data, so F values for shuffled data, and we see most of these are lower than our original value, so this corresponds to a low p-value because we have only few points that show a higher difference, a higher F value than our original value. As I said, PERMANOVA is not assumptions free. So we also have to check for similar dispersion, and a formal test would be like the Bartlett test or the Levine test, for example. Can use the beta disper function. This function takes the distance matrix and an indicator of groups. Same as with Bartlett or Levine. So we can check what's in there now. So we see, okay, here's something eigenvalues and average distance to the median. So we see the distance in downstream sites is slightly higher than in upstream sites. We also saw that on the NMDS plot. And well, eigenvalues indicates, well, it's an eigenvalue based method. You learned about this in the RDA and PCA section. Can also make a box plot of the distances to the centroid. So here we see again downstream a little bit higher distance. We can perform a classical F test using the F distribution. But also here perhaps these assumptions might be not that good, so we can also perform a permutation test. But both give us a p-value greater than 0.005, which says, okay, this slightly difference of 0.04 isn't statistically significant, so this assumption is met in this case. One method that I didn't mention in my slides is a method called SIMPA, similarity percentages. So if you check out the help, so it's !SIMPA, you get to the help file. So SIMPA stands for similarity percentages and shows you which species are responsible for the difference between groups that you observe. So if you're interested, you can just check out here the references, and yes, this function was written by me. So what SIMPA does, it simply decomposes the Bragg-Curtis distance, because as you know, the Bragg-Curtis distance is a summation over species. And here we see all species summed up. And we see, okay, species 19 contributes the most to the difference that we observe. And in fact, this species is upstream much more abundant than downstream. The second most important species would be species 37, and so on. Yeah, and that's it for my art part. I put here an exercise that you can do. It's about Bentic community data around offshore installations to get oil and gas. And there's the questions if these oil platforms have an impact. So, yeah, see you on Monday.